Uh, Hi, everyone. Welcome to the QT Colloquium. I'm very happy to have Srivatsan Chakram as our speaker. He graduated from Cornell with his PhD in 2015, where he worked on ultra cold gases and cavity optomechanics. After that, he joined Dave Schuster's group in Chicago to work in superconducting quantum devices for quantum information science, where he did a lot of very good work. And then after that, he joined Rutgers University as an assistant professor, where he has kept going on working on superconducting quantum computing. And today, he's going to talk to us about quantum control strategies for ultra low loss multimode circuit QED systems. And he said that it's okay to interrupt with questions. So please feel free to interrupt with any questions or comments you have. Take it away. Floor is yours.
Yep. Thank you, David. Thank you for the invitation. It's a pleasure to be here and also to see, former friends, former colleagues in the audience. So, um, yes, let me just make my screen full. Actually, are you seeing the full screen?
No, we're seeing
Okay.
now we're seeing the full screen.
Okay, great. Yeah. I'm an assistant professor at Rutgers in New Brunswick, where I started a group about 3.5 years ago. And I'm going to tell you about the work we are doing in trying to build quantum information processors and simulators that leverage multimode circuit QED with very low loss microwave cavities. Uh, so uh, as this audience knows well, quantum computing with superconducting circuits is at a very exciting time, and several industrial groups and academic groups are building rapidly scaling to larger and larger system sizes, like 10 to 100 qubits and beyond. Most of these processors are 2D lattices of qubits with nearest neighbor interactions. While the qubits are noisy at the moment, steps are being made towards realizing quantum error correction using something like the surface code. And these systems are already useful for applications in quantum chemistry, quantum optimization, and quantum simulations. This progress, the backbone of this is Moore's law for superconducting qubits, which is the fact that there's been a steady improvement in the coherence time of superconducting qubits over the past 2 decades. Um, and now transmon qubits have coherence times that approach half a millisecond quite regularly. But still, the best coherence times belong to those of microwave cavities, particularly microwave cavities that are made out of niobium, which recently have been integrated, are starting to get integrated with superconducting qubits. And these cavity modes have coherence times of 30 to 100 milliseconds. And sort of our goal is to build quantum processors where the cavity modes can have these kinds of coherences, and this comes with a control challenge, and that is basically the subject of my talk. So microwave cavities are the best quantum memories that are available in our field. Most of the cavities that are used are bulk machined out of aluminum, and the standard workhorse cavity is this coax cavity, which is a so-called seamless cavity. It is made out of a monolithic block of metal, so this cavity has a quarter wave post, and there's a lambda/4 mode associated with that. Um, and this kind of a mode can be readily interfaced with the superconducting qubit, as has been done originally at Yale and leading to a wide body of work. There's also other kinds of cavities that you can use. That there are now indium plated micro machine silicon cavities or suspended coaxial resonators, which are have a smaller footprint and also now have millisecond coherence times. But all of these coherence times can be potentially much larger with niobium cavities. So these cavities first came to the fore as accelerator cavities that were developed by the group at Fermilab. And we've been trying to, as part of our SQMS collaboration, try to interface them with superconducting circuits, and with the group at Weizmann recently achieving like very nice results. With a cavity that has a slightly different shape, like a mushroom-shaped cavity. So the other advantage of using cavity modes, of course, is that you can encode a logical qubit within a single cavity mode, and this is possible because you have the redundancy arising from higher Fock levels. Also, a cavity has restricted decoherence channel, with the dominant error being photon loss. And this has led to a zoo of bosonic codes, like starting with the CAT code, the binomial code, and more recently the GKP code. Several groups have now demonstrated quantum error correction beyond break-even, where the error-corrected qubit lifetime is longer than the longest-lived uncorrected qubit in the system. All of these error correction schemes have largely been limited by the decoherence of the ancilla. In addition to quantum error correction, there's also been progress in demonstrations of fault tolerance, where the cavity QED systems have been engineered in such a way that ancilla errors lead to no back action in the cavity. And typically, this has been achieved by engineering dispersive shifts and using higher ancilla levels. So our own work in this is leveraging multi-mode cavity QED systems. The advantage of these kinds of systems is that, in these systems, you couple a nonlinear superconducting circuit to a multi-mode cavity. This allows you to do multiplex control of tens of bits with just a few drive lines. It's very hardware efficient. You get a very large Hilbert space for relatively cheaply, which can also be very high coherence. The superconducting circuit is coupled to all of the cavity modes, and through the qubit, you can have all-to-all connectivity. And these kinds of systems are promising for realizing random access quantum memories, building microwave photonic quantum simulators, and as a test bed for multi-mode quantum error correction. So our own variant of the multimode cavity is based on what we call the flute method, which was pioneered by Ravi when he was a student in the Schuster lab. That's where all of this work started. So let me just describe the idea of this. So if I want to build a rectangular waveguide cavity, something like this, this gray region is the metal, and the region in between is the vacuum. This is the fundamental mode of this rectangular waveguide cavity. The wavelength of this cavity mode is about twice the dimension of the cavity. So if I drill a hole through this cavity, you can see that this hole is sub-wavelength, and the field barely leaks out. And then we can just make the entire cavity by just drilling holes, offset holes from the top and the bottom. So we can just take a monolithic block of high purity aluminum in this case, and just create a cavity volume by just drilling holes. And the advantage of this is that it eliminates losses arising from seams in the cavity. Like, you could have made this cavity from two pieces and bolting them together, but then there will be some current crossing the seam, and there's some resistive loss there, which we completely avoid. So you can make these cavities in various geometries, like a cylindrical disk cavities, a cylindrical disk, for instance. And these cavities, we can now reach quality factors of 20 to 150 million. And these cavities can be, they were first developed by Ravi in his thesis work. These cavities can also be very easily made multimodal by just making them longer. So So this is basically the length of this cavity. So if I take this cavity and if I just sort of unwrap it, it sort of looks like this. And so the smallest dimension is the diameter of the hole. The second smallest dimension is how much these holes overlap, and the longest dimension is the length here. So the second smallest dimension sets the cutoff, the lowest frequency mode, and the spacing between the modes is set by the length. So the previous mode was the fundamental mode, and this is the fifth mode with 5 antinodes along the length. The nice thing about this is that you can, it's relatively straightforward to design a wide variety of spectra and spatial distributions. We typically taper these cavities in order to lens the field towards one side so that we can just efficiently couple to these cavity modes using a transmon at the very end. So, so we can build a larger processor out of this. So here we have a long cavity that's our multimode storage register. And over here, we have a smaller cavity that serves as a readout cavity. And the full 3D model kind of looks like this. And if I slice it, here is the transmon bridges the readout cavity and the multimode storage cavity. As you can see, the transmon consists of 2 capacitor pads, and in between them, there's a tiny Josephson junction, which provides all the nonlinearity to control this system. So the electric field of the cavity mode is pointed along the second smallest dimension, and you can see that there's some dipole coupling between the antenna and the 0-point electric field of the cavity mode. So the cavity is just fully made of holes, so we have to be careful with the packaging and making it light tight. In the Schuster lab, we were able to get transmon coherence times of around 80 to 100 microseconds, and similar T2s, and fairly low thermal populations for the transmon. So now this realizes a circuit QED system, except that in this case, we have a fixed frequency transmon, which is off resonant from the cavity modes. So this is in the dispersive limit, and this leads to this kind of dispersive interaction, which of course is what we leverage for readout in circuit QED. So the cavity frequency shifts depending on the qubit state, but at the same time, the qubits frequency depends on the photon number in the cavity. So here we have driven the cavity with the coherent state, and then we are doing spectroscopy of the qubit, and you can see that we can resolve transitions corresponding to each photon number. So, and in the spacing between the peaks in each case is the dispersive shift. So with our kind of multimode circuit QED systems, we can achieve really high cooperativities of around 10 to the 8 to 10 to the 9. And that allows us to do interesting cavity QED experiments. So given that our system is multimodal, like it's now described by a multimode Jaynes-Cummings Hamiltonian, where we can achieve coupling strengths that are on the order of 100 megahertz. In our first device, it was around 40 to 90 megahertz. This led to dispersive shifts that were ranging from about a few megahertz to about 500 kilohertz. And while at the same time, the cavity modes, all of them had a few milliseconds of coherence and T2s of around 2 to 3.5 milliseconds. And if you want to know more about this, you can have a look at our PRL from 2021. So we did a few interesting experiments with this device. One of them was to engineer multimode interactions through photon blockade. So we use a blockade drive to disallow a set of states in the Hilbert space of this multimode cavity. So let's first consider the simple case of a single cavity mode. So in this case, I have a single cavity mode that is dispersively coupled to a transmon. And you can see that So G and E represent the transpon state, and 0, 1, and 2 represent the Fock states of a particular cavity mode. And you can see that the G2E2 and G1E1 transitions are different by the dispersive shift. And as I showed you before, we can resolve all of these transitions. So we can selectively drive the G2E2 transition. So when we do this, what happens is that in this drive frame, the G2E2, G2 and E2 levels are on resonant, and they're coupled together, so they split. So in the process, the cavity inherits a nonlinearity. So now if you drive the cavity with a drive strength that is much smaller than this, the Rabi drive that was used to create the blockade, then the cavity can't go from 1 to 2 and instead just goes back to 0. And this leads to the cavity undergoing a Rabi oscillation. So we're just driving the G2E2 transition and simultaneously driving the cavity, and we see that there's a Rabi oscillation happening. We can also, through the machinery of a circuit QED, we can also measure Wigner functions. And here's a movie of the Wigner function of the cavity state, starting from the vacuum and going to Fock state 1. Here, the blockade corresponds to in these Wigner functions, the x-axis is position, the y-axis is momentum, and this circle corresponds to a constant energy. So a circle of radius √2 corresponds to blockade of level 2. So what's happening is that the cavity state kind of bounces off of the circle, interferes with itself to create Fock state 1.
Sorry.
Okay, so we can use this to generate multimode entanglement. So here what I'm showing you is two cavity modes after having driven them independently and doing spectroscopy of the qubit. And you can see that each of the modes has a different dispersive shift. Now, if I apply a blockade drive at the G11, E11 transition of the transpon, it simultaneously blockades both the cavity modes. So now if I have this drive on, and if I drive both the cavities simultaneously, and if I measure the population of all of the Fock levels, what you can see is that we started in the vacuum state, and we never reach 2 photons in either of the cavity modes. So what happens is that it goes to a superposition of 0, 1, and 1, 0. So we generated an entangled state just by having this blockade drive on, and then creating cavity dynamics just with the cavity drive. And we can, of course, do Wigner tomography, in this case, multimode Wigner tomography. It's a straightforward generalization of the single mode Wigner tomography, where we displace all of the cavity modes and then measure something akin to the joint parity. It doesn't need to be the joint parity. As long as you know what you're measuring, you can reconstruct based on those measurements what the most likely density matrix was. So you can see here that the cavity we are preparing a Bell state between the two cavity modes, and we use this to prepare like W states of up to 5 modes. So that was a way in which we could generate entanglement between multiple cavity modes. But how do we do universal control? There are a wide variety of schemes for doing this, but they all rely on the Josephson nonlinearity and the dispersive interaction. So the Hamiltonian is the same, but we use different paradigms for control. These include resonant charge sidebands, snap gates, and optimal control, photon blockade, which I described, and more recently developed conditional displacement gates. So these are all different ways in which you can perform universal control on any of the cavity modes. But the message of the talk is that certain control schemes are better for controlling multi-mode systems and very, very low loss cavities. So let me explain that. So the main challenge is that while the cavity modes are very pristine, coupling them to the ancilla leads to errors induced by the coupling to the ancilla. So this includes the inverse Purcell effect, which is that the pristine cavity inherits the ancilla's decay by virtue of the coupling. So this goes as the T1 of the cavity modes is delta squared by G squared times the T1 of the ancilla. So additionally, during all of the gate operations, the ancilla gets excited. So the ancilla has some decoherence during the gate. So the thing to note here is that the other thing I want to say is that in the context of a multimode system, the coupling to the ancilla also leads to the cavity modes inheriting nonlinearity and or even this the dispersive shift itself. So basically, you want to use the ancilla to perform operations on one particular cavity mode, but the ancilla's frequency might be different depending on the occupation of another spectator mode. So in general, you want to increase the chi in order to decrease the decoherence during the gate, but you want to decrease the chi in order to both mitigate crosstalk and mitigate the inverse Purcell effect. So what is the way around this? So I'll be sort of exploring three different solutions, or our group is exploring three different solutions. I'll be mostly focusing on the first one in this talk, which is to weaken the chi, but do gates that scale faster than chi. Okay, so at Rutgers, we have now realized these kinds of multimode memories with a weakly coupled transmon. So this is very similar to the device I showed before, except that we have a separate transmon drive, and we have weakened the coupling. So we now have a transmon coupled to our readout cavity as well as to our multimode storage cavity. And this transmon we got from our collaborators at the SQMS Center at Fermilab. And the transmon has decent coherence times, and we use the knowledge we gained from making the Schusterlab devices light tight to achieve low thermal populations of the transmon. So we were able to get like thermal populations of 0.2 to 0.4%. So these are the T1 and the T2s of the cavity modes. So the T1 is around, a millisecond to 750 microseconds, and the T2 is pretty close to 2 T1. Crucially, we've lowered the coupling. The chi's are around 200 kilohertz, so that the Purcell limit of the cavity modes is 60 milliseconds. Okay, so how do we achieve fast gates with weak coupling? So there are two strategies. One strategy is to use large displacements of the cavity to enhance the interaction rate. And the other strategy is to use large displacement of the ancilla to increase the interaction rate. So let me start with the first one. So this was first developed in the Devere group, though there were precursors to this also from Irfan Siddiqui's group. So basically, if you displace the cavity, then essentially that displacement acts like a lever arm. So the displacement in phase space gets larger. Another way of looking at this is that if you take this dispersive interaction and go to the displaced frames, then your chi A dagger A sigma z becomes chi alpha A plus A dagger sigma z. So your gate speed goes from chi to chi alpha. And then the so-called echoed conditional displacement is a symmetric pulse on both the qubit and the cavity. It's a simultaneous qubit cavity echo that allows you to isolate the conditional displacement while echoing out other spurious terms. These kind of this gate can be extended to the control of multiple cavity modes by just sequentially acting ECD gates on each of the cavity modes. So you do a qubit rotation, ECD gate on mode 1, qubit rotation, ECD gate on mode 2, and you can construct an arbitrary unitary by just a series of qubit rotations and ECD gates. And there's also a related multimode C0 gate scheme that was developed by the group at Technion, which has interesting relations to this. Our collaboration with Fermilab, we've been looking at using optimal control pulses on the qubit that are robust to detuning errors, and find that using these qubit pulses instead of regular Gaussian pulses or even drag pulses leads to mitigation of this crosstalk error. So you can see that the fidelity of the state barely changes as you put photons in the spectator mode. Okay, so the main meat of this talk is our work on exploring these charge-driven sidebands. So the transmon, as you all probably know, is a particle in a cosine potential. And the lowest order nonlinearity is a quartic nonlinearity. And this allows you to do four-way mixing processes. So in particular, you can have a process where you can have two photons in the transmon get converted into one photon in the resonator in the presence of a drive. Another way of looking at this is that if you drive the system, and if you go to the rotating frame of the drive, then you can make the F0 and G1 state resonant. They're not coupled to each other, but they do have a virtual coupling mediated by the E0 and E1 levels. And actually, these two paths destructively interfere to lead to some virtual hopping between the F0 and G1 states. So this you can do this perturbation theory, and you can see that this sideband swap rate is actually linear in the drive and linear in G. So you can write this as epsilon times chi over G. So by increasing the drive strength, you can actually do gates that are faster than the dispersive interaction strength. So for instance, in our system, the dispersive interaction strength is around 200 kilohertz, and we are able to do these swaps with any of our cavity modes in about 200 to like 600 nanoseconds. So this is a swap rate of around 3 to 5 megahertz, which is beats our dispersive coupling to the E state by a factor of 25. So in order to achieve this, we're actually driving the transmon quite hard. So the transmon drive strength is on the order approaching a gigahertz, and the transmon displacements are around about 0.2 to 0.5. Additionally, the drive frequencies are quite low. They're on the order of 1 to 3 gigahertz. So we are approaching a limit where the rotating wave approximation definitely breaks down, and perturbative methods don't quite work well. So we've been understanding quantitatively matching our start shifts and swap rates by using Floquet methods. The other thing that we have had to keep in mind is that at these large drive strengths, it's important to stay adiabatic between your rest states and the Floquet quasi-energies. And we've been doing a lot of optimization of this. So you can do this F0 G1 sideband in the one photon manifold, but you can also do this, you can also climb up the Jaynes-Cummings ladder in this way. So you can have transitions from Fn to Gn plus 1. These transitions are all different by the dispersive shift of the F state. So this is the F0 G1, F1 G2, etc. And all of these rates, because of the bosonic enhancement factor, are different by square root of n. So the F1 G2 is root 2 times faster, etc. So you have the square root of n speed up. So how do we prepare states in the cavity? You can just climb up the Jaynes-Cummings ladder. So you can go G0, E0, F0, then swap to mode 1, and then you can repeat this process. And this allows us to um, um, basically prepare Fox states. And you can also similarly prepare superpositions of 0 and 0 plus n, for instance. The key trick is that you have to shelve the state. So this data is actually just fresh off the oven. We just got this yesterday, but so these are sort of the best fidelities we have so far. We still need to do further optimization to get the calibration right and minimize leakage and characterize our tomography errors. So this is just a particular protocol that we use to prepare Fox states and 0 plus n states, but actually this fits into a more general paradigm. So the sideband drives lead to an effective Jaynes-Cummings interaction, which is tunable. And here, the sigma minus, the Pauli operator, is between G and F. So this actually maps onto a very famous state preparation scheme, that's the Law-Eberle scheme, which was originally developed in the context of controlling motional states of trapped ions, and also has been demonstrated in superconducting circuits where a resonator is coupled to a phase qubit. This is a famous experiment from the Cleveland group from 2009. So we can use these the Law-Eberle protocol to prepare states in any of our cavity modes. So let me just explain this protocol. So if you want to prepare an arbitrary state consisting of a superposition of up to n photons, you can do this with just n sidebands and n qubit rotations. So the protocol is that if you want to make a unitary, you just try to do the time reversed unitary, run the unitary in reverse, like see what you need to do in order to take this state of interest into vacuum. And in particular, how you do it is you remove one photon at a time from the state, and this leads to a set of algebraic constraints that allows you to find an analytic pulse that does this. The nice thing about how this scales is that because the sideband on the Fock n is faster by root n, this has a sublinear in n scaling. So this protocol is great for state preparation, but unitaries are more challenging. So in our work, we're going beyond Law-Eberle by leveraging the fact that we still have this dispersive shift. So we've used this our sideband control to prepare basically the fiducial states of the binomial code. So the binomial code is kind of the simplest bosonic error correcting code. The down logical qubit is Fox state 2. The up logical qubit is a superposition of 0 and 4. When you have photon loss, 2 goes to 1, 0 plus 4 goes to 3. Because the two states have the same mean photon number, the coefficients of the superposition do not change. You can use parity as the syndrome to detect photon loss. And QEC was achieved beyond break-even in 2023. There have been a wide variety of two-mode gates that have been implemented between bosonic qubits. All of these experiments, though, have been done in a regime where the dispersive shift is large, around a megahertz. So we've been exploring doing this in the limit where this dispersive shift is weak, so that we can apply these protocols to very, very high Q cavity systems, like cavities like the niobium cavities that I had mentioned at the beginning of the talk. So we've used this protocol to create binomial code states in the first 7 of our cavity modes. This is still a bit, this data is still a bit old. Right now, our fidelities are about 5% better. So this is just state preparation. How do we perform unitary operations? So one of the problems with the Law-Eberle protocol is that it entangles these Fn and Gn plus 1 transitions at incommensurate rates. So you have to you want to do a transition on one particular fork level, but the other one doesn't do a full rotation or does some rotation by some incommensurate angle. So we go around this by developing photon number selective sideband transitions. So the basic idea is that if you drive a sideband transition with some detuning, then while the contrast is going to be lower, right, the speed is also going to be uh, uh, commensurately faster. So you can pick the sideband rate to be such that you do a pi rotation on one level while doing a 2 pi rotation on the other. So using this idea, we can, for instance, you can do a pi sideband on the F1G2 transition while doing a 2 pi sideband on the F3G4 transition, etc. So using this, we developed an encoding sequence for our binomial code state. So this encoding unitary, what it does is that it takes an arbitrary superposition in the transmon to an arbitrary superposition or corresponding superposition of binomial code states. So the unitary itself is hard to explain, but the key pieces are these photon number selective sidebands. So in this case, we're doing this encode operation with only sidebands and transmon G and EF pulses. In this case, the whole encode operation happens in about 4 microseconds or so, which is still faster than 1 over chi. So we can, of course, start the qubit at all of the cardinal points on the block sphere, and we see that the unitary works. So starting in G, we prepare Fock state 2, and the same pulse sequence takes the qubit in E to a superposition of 0 and 4, etc. And we can similarly start the transmon in arbitrary superposition states. So the fidelity is still being optimized, but it's around above 85%, like 88 to 93%. Right now, the error budget is still like dominated by transmon decoherence. We're still optimizing the residual sideband leakage that's arising from us not being adiabatic. We still have to optimize the attenuation and filtering, have to do better pulse shaping, etc. And where we are going with this is that we're starting to prepare entangled binomial code states, and with an eye towards doing like an extra layer of error correction, perhaps a repetition code of binomial qubits. Okay, so that was our experiment where we had a vanilla multimode cavity just coupled to a transmon, albeit weakly. The real way in which we can get rid of crosstalk error in multimode processors is, I think, a different architecture, where instead of interfacing our multimode cavity directly to superconducting qubit, you instead use a processor module. So here you have your transmon, which is the central processor, coupled to a processor cavity, and it's this processor cavity that interfaces with the multimode memory. In this case, the entity that does this interfacing is a tunable coupler. So that is still a superconducting circuit, but it's operated in a very different way. It never is physically excited with a photon. It just virtually mediates the coupling between the processor cavity modes and the modes of the multimode memory. So what's the anatomy of a gate? You swap your cavity state in your target cavity modes into the processor cavity, do some operation using the nonlinearity of your superconducting ancilla, and then you swap back. So again, the advantage of this is that the tunable coupler is only virtually occupied, and the coherent error, which was previously given by the dispersive shift, is now reduced to the cross curve between the coupled cavity modes. So it's this crosstalk error is reduced by a factor of 10 to the 5. So a similar architecture is also being developed in the Schuster lab and much further along. So our own vision for this is to next replace this transmon with the fluxonium. And we expect that given that the fluxonium has higher coherence, we can potentially achieve higher gate fidelities. So this is prototype of our multimode module with a tunable coupler. In this case, the tunable coupler is implemented using a snail circuit. So the snail is a circuit that consists of one small Josephson junction in parallel to 3 large Josephson junction. The advantage of this circuit is that you can bias it at a point where it has a large cubic nonlinearity, as opposed to the transmon where the lowest order nonlinearity was quartic. The advantage of this cubic nonlinearity is that you can activate fast beam splitter by just a single drive tone acting at the difference frequency between the 2 target cavity modes. And there have been experimental demonstrations from the Sholkoff lab where such snails have been used to perform like high fidelity beam splitters approaching, exceeding 3 nines. And there have also been experiments from the Hartridge group. So this is a prototype of our module. So it's similar in that we have, this is our multimode cavity register. This is our processor cavity. So it's again a rectangular cavity, but in this case, it's 2 coupled cavities. And zooming in, we have our snail that bridges the processor cavity and the multimode cavity. The main challenge in doing this is that the way we achieve tunability typically is by applying magnetic fields through a squid or a snail. And in this case, we have to do it while maintaining the very high coherence of the cavity. And the whole thing is in a superconducting cage. So the way we do this is by using what is called a flux transformer. So essentially, we have our bobbin that sets up a field. That field sets up a persistent current in a superconducting loop, and the current that persistent current is used to drive flux through the snail. So we've designed this system to have the processor modes be below the storage modes. This is just a detail. Basically, we just optimized the cavity frequencies and couplings in order to achieve what we hope are fast enough swap rates. So right now, these experiments are underway. We have our new multimode processor where the cavity coherence times are decent. They're again still made out of aluminum, so they're still millisecond level. But right now, the snail-mon integration is underway. Okay, so that's this is our path for realizing a multimode module that is free of crosstalk. So how do we scale the system up? Basically, we want to couple different multimode modules together. So our roadmap is that we have eventually we'll have the buffer cavity or our processor cavity be controlled with the fluxonium, and then we'll have a remote entanglement between 2 fluxoniums and use that to do a teleported gate. So this is an ARO project that is a collaboration between my group and that of Wolfgang, Angela, and Sham. So I think I'm close to the end. So just to summarize, the control of really high Q cavities or multimode cavity QED systems requires mitigating ancilla decoherence and crosstalk. A promising strategy is to weaken the coupling and perform gates that are faster than the dispersive coupling. We've managed to demonstrate fast control of a multimode memory with a weakly coupled ancilla. Our control protocols are sort of inspired by the Law-Eberle-like schemes, and we've sort of generalized that and gone beyond that to realize unitary gates in the context of here the binomial encode operations. We're also developing error-resilient multimode processors with tunable couplers. So with that, I'll just thank my the lab I was the Schuster lab where I was a postdoc, where all of this work stemmed from, as well as my collaborators at the SQMS Quantum Center, and Wolfgang, Angela, and Sham, and also my thank my group. We're a young group, and we're looking for interested undergrads, grad students, and postdocs. So if you find any of this work interesting, please send me an email. Thank you.
Okay, let's thank Srivatsan for a very nice talk. Yeah. Are there any questions, comments?
I have a couple of questions. Thanks again, Watson. That was a great talk. Really enjoyed that. And super exciting where this is going. I'm curious about your perspective on gates between multiple modes, so between two modes, whether these beyond chi schemes would translate to those as well. I think you're most looking at single mode manipulation. So I'm curious how that applies to multi-mode operations.
Right. So actually, I didn't present on this, but like the current experiments that we are running are going towards making noon states. So that's still, it's not a gate, but it's generating entangled states. So there you can kind of just instead of doing sidebands on one mode, you can do sidebands on the other mode. You can basically put the qubit in F, put half of it in one mode, put the rest in another mode, and climb up the ladder. So this allows you to make noon states. So with this encode operation, you can always I can always decode to the qubit, right? And then I can do a gate with another binomially encoded mode by doing a resolved pi pulse, right? Which is basically a C0 gate with the cavity as the control, right? So a resolved pi pulse is C0 gate with the cavity as the control. So then if I decode and then do that gate, then I basically can do a C0 gate between any of the binomially encoded qubits. I mean, this might not be a good idea because you're decoding, but that would be a way in which you can do gates between binomially encoded qubits in any of the cavity modes. So we're trying to, this kind of law-Eberle way of doing things, it seems very fast, and it's what worked best for us, right? But I think there are questions about how to make this fault tolerant, right? So which are not very obvious with thinking about this, but we don't have good answers yet. But I mean, what I told you was a way in which you can do gates between binomial qubits stored in different modes. Yeah.
Okay.
I have more questions, but I'll wait for if anyone else does.
Any other questions, comments? Then go ahead, Ravi.
So you mentioned using fluxonium replacement for the transmon, and a strong part of what you're using for a lot of these Eberle schemes was leveraging the nonlinearity of the transmon to be able to do these gates. And generally, we think of fluxonium as a much more nonlinear system, like a severe increase in that nonlinearity. What impact would that have on these schemes, do you think?
Right. So I think with regard to like the sideband control schemes, I think it's kind of hard to have, especially at half flux, have direct coupling with a resonator, right? So that's not allowed by selection rules. But you can have these snail fluxoniums, right? You can have like this is work from the Devray group, but also recently Angela's group has made a lot of progress on this. So you can have the fluxonium L interrupted with a snail, and this allows you to do three-way mixing. So probably if you want to use just this sideband-like control to perform gates on cavity modes using a fluxonium, I would probably I'm thinking that direction is probably the direction to pursue. But of course, if you have a fluxonium coupled to this to a cavity, you can also use the more standard schemes, like you can just use snap gates or ECD gates. So I would say like maybe the snap gate seems like the most straightforward to me, because one can engineer a chi that is around 0.5 megahertz between the fluxon states at half flux and a resonator, right? And then the nice thing about the snap is that the cavity drive, the qubit drive, anyway, it's not going to be that strong. It's going to be comparable to the chi, right? And so it's very hard to charge drive the fluxonium, but maybe for a snap gate, it doesn't matter as much, right? And regarding ECD gates, there, you have you're doing these ancillar rotations, and they need to be fast otherwise the echoing doesn't work as well, right? So there, you still need to be able to do fast fluxonium gates. So.
Okay. Any other questions or comments? Then let's thank our speaker again. Thank you very much for a very cool talk.